So what you're looking at here is a classic representation of our critical system failure. We've got a solid, high-quality shielded cable, yet it is radiating electromagnetic energy all over the place. And, on the flip side, it's highly susceptible to picking up noise from the outside environment. But the shield is completely intact. There are no holes in the middle of the cable, so where exactly is the leak coming from? To understand how this happens, we need to look past the macro surface of the system and dive straight down into the micro-level physics inside the cable shield itself.
Moving right along to Part 2, Core Concept, Shield Current Flow.
According to electromagnetic compatibility expert Henry W. Ott, the magnetic shielding effectiveness of a cable depends entirely on one crucial thing: a uniform distribution of the longitudinal shield current around the entire circumference of the shield. But take a look at what often happens at the ends of the cable. Engineers will strip back the outer insulation, gather up the braided shield, twist it into a single wire, and solder it to a pin. We call this a pigtail. And as our definition right here shows, a pigtail completely destroys that uniform 360-degree current distribution. It does this by forcing all that longitudinal shield current to concentrate on just one side of the shield.
Let's make this concrete with a visual analogy you will absolutely never forget. On the left, we have figure 240, which shows that pigtail connection we just talked about. On the right, figure 241, a disassembled BNC connector that gives you a full 360-degree electrical contact to the shield. Now, I want you to imagine voltage as water pressure and current as a massive volume of water rushing through a wide pipe. That BNC connector on the right, it's like the open end of that wide pipe. The water flows out smoothly, evenly, with literally zero restriction. But the pigtail on the left, that is like taking that exact same massive, wide pipe, capping the end and forcing all that rushing water to squeeze through a tiny, high-pressure funnel on one side. It creates this massive turbulence and back pressure. In electromagnetic physics, that back pressure is called inductance. By forcing the current into a single twisted wire, you've just created a highly inductive bottleneck.
Which brings us to Part 3, the math of shield coupling.
All right, let's look at Figure 2-44. This plots experimental data for a 3.66-meter shielded cable that has an 8-centimeter pigtail at both ends. And the circuit termination here is 50 ohms. Let's break down exactly what this math is telling us. On the y-axis, we have the voltage transfer ratio. Mathematically speaking, this is the ratio of the noise voltage induced in the center conductor over the source voltage on the shield. Simply put, a higher number means a worse leak. Down on the x-axis, we have frequency, scaling logarithmically from 100 Hz up to several megahertz. Now notice the three distinct curves. The top dashed line, that's the total experimental coupling. But look closely at the solid lines breaking it down. You've got shield inductive, pigtail inductive, and way down near the bottom, pigtail capacitive. Because our circuit impedance is a very low 50 ohms, capacitive or electric field coupling is pretty much negligible here.
Now, what's really fascinating about this slide is what happens right at the 100 kilohertz mark. Below 100 kilohertz, the primary noise leak is just the natural inductive coupling of the shield itself. No big deal. But as soon as we cross 100 kilohertz, look at how that pigtail inductive curve just shoots straight up at a steep angle, physically overtaking the shield's own coupling. The math here proves that above 100 kilohertz, that tiny 8-centimeter piece of wire, our little high-pressure funnel from earlier, becomes the absolute dominant source of magnetic noise coupling for the entire 3.66-meter cable.
Okay, Part 4, Walkthrough, Solving a Problem.
Let's walk through a real-world design problem step by step. Step 1. We just analyzed a low-impedance 50-ohm circuit where the pigtail acted as an inductive magnetic loop, right? Well, step 2, what if we're designing a higher impedance sensor circuit? Let's say we increase the termination impedance of our shielded conductor from 50 ohms up to 1,000 ohms. Step 3, we need to calculate the new coupling dominance. Based on standard electromagnetic theory, higher impedance circuits are far more susceptible to capacitive, meaning electric field coupling. So let's look at what the data actually says. Boom! Figure 245 brilliantly illustrates this physical shift. It's the exact same experiment as before, but now with a 1,000 ohm termination. Look closely at the curves on this graph. The shield, inductive, curve actually flattens right out. But check out the pigtail, capacitive curve. It literally rockets upwards, completely dominating the entire noise profile for any frequency above 10 kilohertz. This is wild. By just changing the circuit impedance, we drastically change the underlying physical coupling mechanism. That pigtail is no longer just a magnetic funnel. It's now acting as a highly efficient capacitive antenna, pulling raw electric field noise directly into our sensitive 1000 ohm circuit.
Let's quantify just how bad this failure really is. At 1 MHz, look at where that capacitive pigtail curve lands, compared to where the shield's baseline inductive curve sits. The gap between them is exactly 40 decibels. Now let's translate that math into reality. A 40 dB increase in voltage transfer ratio mathematically means 20 times the log base 10 of V2 over V1 equals 40. Divide both sides by 20 and you get 2. 10 to the power of 2 is 100. That means the noise voltage injected into your circuit is exactly 100 times greater, purely because you used an 8 cm pigtail instead of a 360-degree BNC connector. One lazy solder joint literally multiplied your system noise by a factor of 100. Let that sink in.
That brings us to part 5, the high-frequency pigtail pitfall. So why does this happen? The trap here is largely historical. You'll see veteran engineers often rely on pigtails because, back in the day, or in purely low-frequency audio applications well below 10 kHz, a short pigtail is kind of acceptable. At those low frequencies, the pigtail's inductance doesn't create enough impedance to totally ruin the shield's performance. But today's digital circuits, they operate well above 100 kHz, often pushing deep into the gigahertz range. And as we just saw mathematically, at those high frequencies, that exact same pigtail completely falls apart. It acts as a massive inductive bottleneck and a powerful capacitive antenna. It's just a fatal design flaw for modern EMC.
So the absolutely crucial point is this: how and where do we actually terminate? Well, High-Impedance is very explicit about this rule. If your cable shield picks up high-frequency RF noise, you must terminate that shield to the outside of the equipment's metal enclosure using a 360-degree connector. Never terminate it to your internal circuit ground. Think about it. If you dump all that RF noise onto the internal circuit ground, it's just going to pollute your sensitive electronics and your whole system fails. But if you tie it to the outer enclosure with a low-impedance 360-degree bond, that RF noise flows harmlessly over the outside surface of the box, passes through parasitic capacitance, and goes safely down to earth ground, entirely bypassing your internal electronics. It's a real game changer.
Finally, Part 6, Summary and Final Takeaways.
Okay, here is your rapid-fire survival guide for today. Number 1. 360-degree uniform terminations, like BNC connectors, are absolutely mandatory for high-frequency EMC to prevent the funneling of current. Number 2, pigtails are fatal at high frequencies, mathematically adding up to 40 dB, or a 100x multiplier, of inductive and capacitive noise coupling. And number 3, the enclosure rule. Always terminate your cable shields to the outer chassis enclosure, never to your internal circuit ground. As High-Impedance states in the text, the maximum benefit of a well-shielded cable will only be realized if the shield is properly terminated. Look, an expensive cable is completely worthless if you just choke it with a pigtail. Keep that foundational rule at the front of your mind on your very next design. If you found this engineering deep dive valuable, hit subscribe for more EMC and automotive communication protocol survival guides. What's the absolute worst EMI failure you've ever had to debug? Leave a comment below, and until next time, keep your ground solid and your shields intact.